Hello, hello. Oh, ahí está, perfecto. Y ya es todo. Ya. Ok, ahora sí, mi chiste. Ahí viene. Nayem, gracias por decirme.
Good grammar and
Neta.
spelling are important, but if you want to write
Esto,
essays
esto
that
no es.
inspire.
I don't know what you heard about me, but a bitch can get $1 out of me. No Cadillac, no perms I can't see. Welcome to the motherfucker STRAME. Bienvenidos al stream. Gracias. Nayem, mientras tú también deberías estar estudiando, siendo honesto. Ahorita estás en clases y eso es verdad. Pero no, estás viendo a Kiros Gaming porque es tu youtuber favorito. Ya, pues a estudiar, a estudiar. Estudiar, estudiar. Como van arriba, ahí están mis tasks. Parsons te va a matar, en serio. Spamea el link de mi stream al Zoom. Te reto poner mi link al link del stream en el Zoom. Y te pago 100 pesos si lo haces. No Cadillac, so. So no motherfucker STRME. Ok, pues voy a hacer. Primero, tarea que voy a hacer es mi tarea de física. Ir al loto. No, está bien. Tú dile si quieres.
And what do we have down here, gang? We have some plates. No staples, no Velcro. The tablecloth. This is what I want you to do over the weekend when you get invited to dinner at someone else's house, okay? What you do is they say, hey, what are you learning at the university? Say, I'll tell you what I've been learning at the university. Okay? And get the table all set. Grab the tablecloth like this and say, do you believe in the first law of inertia? And they say, yes, we do. Hey, how about that?
Welcome to the European Space Agency ESA. This is the Robotic Learning Centre, and I'm here to help you find out more about Newton's 3 laws of motion. Maybe you've heard of Newton before. He is the scientist who got hit on the head with an apple. At that time, he was studying motion, trying to understand the concepts behind it and how they relate to things we experience in everyday life. When Newton recovered, he realised something important. He already knew that an object accelerates only when a force acts on it. Therefore, if the apple were moving, it could only accelerate if there was a force acting on it. He called this force gravity, and to this day we measure all forces, including gravity, in newtons. Newton came up with 3 laws of motion, laws that describe how forces and objects relate to each other. To help you out, I've asked some friends in Barcelona, Dublin, and Erlangen to demonstrate the laws. I've also asked astronauts on board the International Space Station to help us. That's the ISS for short. So we're going to hear from Pedro Duque and Alexander Caleri. On board the ISS, gravity has very little effect, so everything there is almost weightless. Hi Pedro. That's a nice smile you've got there, Pedro. Not much is happening. The ball is just hanging there in midair. Pedro blows on it and it moves because of the force of his breath. Now the ball is moving again, except this time Alexander has stopped it with his hand. And this time, nice move. Pedro changes the ball's direction by applying a force. What you've been seeing are illustrations of Newton's first law of motion. This states that every object in motion or at rest remains in that state unless an unbalanced force is applied to it. The state of motion is the speed and also the direction. The two combined, speed and direction, are what we call velocity. An object at rest has a velocity of 0, and it stays at rest unless acted on by a force. We call this tendency inertia. Here you can see Pedro applying a force to the ball. He is changing the ball's direction, therefore changing its velocity. In the second experiment, you see Alexander stopping the ball. Here he's changing the speed, therefore he's changing its velocity. The rate of change of velocity is called acceleration. Let's see what our schools have to show us. Pushing the skateboard, that's a force, isn't it? The skateboard moves, hits the pillar and changes direction. But the apple keeps going. That's because this time the force is only applied to the skateboard and not the apple. That's why eating in space isn't easy. The spoon stops, but the food keeps going.
Oh, sí es cierto.
Ooh, that looks nasty. And that's why we use seatbelts. If we were in a weightless environment like the ISS, then he would continue to move. But on Earth, gravity pulls him back down. Okay, here we go again. That looks really messy. That's why we have to use lids on takeaway coffee. Thanks, girls. Good trick. I'm sure I don't have to say, don't try this at home. Looks like she's getting her teacher in to help. That apple's not going anywhere. I mentioned objects at rest, didn't I? In these experiments, the apple, the pencil, and the girl on rollerblades are not moving. They're at rest because the forces acting on them are in balance with each other. But when the support is removed, the force of gravity, now unbalanced, pulls them to the ground. Without the force of gravity, they would just stay afloat, just like on board the ISS. So, that's Newton's first law. An object at rest stays at rest unless acted on by a force. And an object in motion will stay in motion unless acted on by a force.
I'm not just watching videos right now, if you guys were wondering. Video time. You guys want to see the videos? Let's see the videos. Okay, not do that. Alright, I can do this, I can do this. Let's get a glass, a coin. We have coins. Glass, coin. Is that a sheet of paper? Is that like a card? SCIE. What is this, like subliminal message? Alright, let's do it. I'll be right back, guys. Okay. You got her thing. I'm gonna do it off cam. Well, I can put the cam like that. Boop. And motherfucker. Alright. Let's do it. Yep, it works, it works. Wait. Okay, I know how to. Oops. Put the focus on it. Oh fuck, yeah, I'm gonna break my iPad one day. Okay. Hello, I'm going to be explaining Newton's first law of motion. So over here we got a dime and a cardboard cutout. And I know it doesn't like go through all the way, but that's alright, I can still get the point across. So the dime is in the cup. It's on the top of the cardboard. So if I flick the cardboard, it drops down. And that is because the dime was stationary on top of the cardboard, and when I flicked the cardboard, it was no longer stationary. I applied motion to this cardboard, and I didn't apply motion to the dime, so it fell down. That's it. I don't know why it took me so long to make this video. Thank you. Mi nombre es Naomi, Naomi Yaratzel. Alright, kidding. That was loud as fuck. Oh my god, it said 20 seconds. I'm going to be explaining Newton's first law of motion. So over here we got a dime and a cardboard cutout. And I know it doesn't like go through all the way, but that's alright, I can still get the point across. So the dime is in the cup. It's on the top of the cardboard. So if I flick the cardboard, it drops down. And that is... How do I make it short? So if I flick the cardboard, it drops down. And that is because the dime was stationary on top of the cardboard, and when I flicked the cardboard, it was no longer stationary. I applied motion to this cardboard, and I didn't apply motion to the dime, so it fell down. That's it. I don't know why it took me so long to make this video. Thank you. Alright. I sent it to Gmail. Gmail changed logos. That's so cool. That's weird. What? It's not changed on just the app. It's changed. Oops. All right. So Google Drive it is. Can't upload this many megabytes to Gmail apparently. So upload this. Go to Google Drive. And then just go to my drive and then go to this drive and then let's go. What's that called? Good notes. We did one homework! Hey! I'm cringe. I'm just kidding. Fuck that. Where's my underscore? Activity P15.
I'm going to show you some examples of how to solve problems involving work. Imagine a 4-kilogram trash can. The trash can is disgusting, so someone ties a string to it and pulls on the string with a force of 50 newtons. The force of kinetic friction on the trash can while it slides is 30 newtons. The trash can slides across the ground for a distance of 10 meters. Let's try to find the work done by each force on the trash can as it slides across the ground. To find the work done by each force, we should recall the formula definition of work. Work equals FD cosine theta, where theta is the angle between the force doing the work and the direction the trash can is moving. There are 4 forces involved here: tension, the normal force, the gravitational force, and the force of kinetic friction. In finding the work done for all of these forces, the displacement is going to be 10 meters, but the value of the force and the angle between that force and the displacement is going to differ for each of the forces. For instance, to find the work done by the force of tension, we'll plug in the size of the tension, which is 50 newtons, the displacement is 10 meters, and since the tension force is pointed in the same direction as the displacement, the angle between the force of tension and the displacement is 0
So you just
degrees.
multiply them. Yeah, you
Since
just multiply
cosine
them.
0 is 1, the work done by the tension force is
This is
500
50,
joules.
yeah, pretty
To find the work
simple
done by
actually.
friction, we'll plug in the
Let's
size
see.
of the force of friction, which is 30 newtons. The displacement is still 10 meters, and since the force of friction points in the opposite direction as the displacement, the angle between the force of friction and the displacement is 180 degrees. Since cosine of 180 is -1, the work done by the force of friction is -300 joules. Now let's figure out the work done by the gravitational force.
What are the forces acting on paint cam? Which forces are doing work? Are there any cases of friction? Let's
The
talk
force of
about
gravity
that.
is mg, so the force of gravity is 4 kilograms times 9.8 meters per second squared, which is 39.2 newtons. The displacement is again 10 meters, but the angle between the gravitational force and the direction of the displacement is 90 degrees in this case. And since cosine of 90 is 0, the gravitational force does no work on this trash can. Similarly, if we were to find the work done by the normal force, the angle between the direction of the displacement and
So
the
yeah,
normal
it's on
force is 90
X.
degrees.
If it's
So the normal
somewhere
force
else that
also
is
does
not
no
X,
work on the trash can.
0.
This makes sense because forces that are perpendicular to the motion can never do any work on that object. So that's how you can find the work
But can the motion be upward though?
done by individual forces. And if we wanted to know the net work done on this trash can, we could just add up the work done by each individual force. So the net work is going to be 200 joules. Now that we know the net work done on the trash can, we can use the work energy principle to figure out the speed of the trash can after it slid the 10 meters. The work energy principle says that the net work done on an object is equal to the change in kinetic energy of that object. So 200 joules is going to equal the difference in kinetic energy. If we assume the trash can started at rest, which seems reasonable, the initial velocity is 0. So we can solve for the final speed of the trash can, which comes out to be 10 meters per second. This time, let's say you take the trash can and lift it upwards with a constant velocity for a distance of 2 meters. In order to lift the trash can up with a constant velocity, you need to push with a force equal to the weight of the trash can, which means you have to push upwards with a force of 39.2 newtons. So to find the work done by the force that you exert, the force is going to be 39.2 newtons, the displacement is going to be 2 meters, and the angle between the force and the displacement is going to be 0 degrees because the direction of the force that you exert is in the same direction as the displacement of the trash can. So the work that you've done in lifting up this 4 kilogram trash can is 78.4 joules. To find the work done by the force of gravity, we can use the force of gravity, which is again 39.2 newtons. The displacement gravitation is again 2 meters, but the angle between the direction of the displacement and the gravitational force is 180 degrees because the displacement points up and the gravitational force points down. So the work done by the gravitational force is negative 78.4 joules, which means the net work done on the trash can is 0. And that makes sense because since the trash can moved upwards with constant velocity, there was no change in the kinetic energy of this object.
And what's the paint can? I'm gonna go crazy. What's the paint can? Do I do? Ask my friends. For cam. Hola. Hola.
Quiroz.
Hola.
¿Qué
Hola,
haces?
Iván.
Hey, Quiroz, ¿estás hablando de Bogat el profe o qué?
Me estaba preguntando si la vio.
Ah,
¿Qué tiene? Tú.
no mames.
Iván. Existe la actividad P15 de química, de physics.
Sí, hice todo según yo.
Ajá. ¿Dónde, tipo, te pide hacer un diagram de una paint can? Pero, ¿dónde?
Espérate, ¿es 15?
Sí.
Déjame checar. ¿Cuándo
Ah,
lo
o
hicieron?
todavía no. Ah, no, me estoy pasando de lanza, no tenemos que hacerlo. Sí, es cierto. Ignora lo que dije. Todavía no lo
¿No lo
tenemos que
hemos
hacer.
hecho?
Ajá, sí.
Ay, Quiroz.
Watching Physics Classroom's video tutorial series on Newton's laws. The topic of this video is drawing free body diagrams. The question we wish to answer is, how do you draw a free body diagram?
Drawing
to
free body
represent the
diagrams is
relative
essential.
strength
Create your own free body diagrams, selecting the forces, and 3 is the situation. I'm so hungry. Alright guys, well, this has been the stream for now. We're gonna probably continue it this afternoon.